Hello, I'm Tim Lichtenberg from Atmospheric Physics at Oxford. I will present the results of my work, published earlier this year in the astrophysical journal Lattice, on the influence of the interior redox state on the secondary atmospheric composition of sub-Neptune and super-Earth exoplanets. I argue that the fluid circulation regime in the internal magma oceans of sub-Neptunes can control the chemical equilibration between planetary metal core, mantle, and atmosphere, which has several implications for surface and atmospheric compositions that we can expect to observe on super-Earth, and the prospects for astronomical characterizations of these types of planets. Here you see an artistic illustration of two members of this wide class of exoplanets that are prime targets for atmospheric characterization. Super-Earth GJ1132b here on the left has been under scrutiny for several claimed detections of an atmosphere in the past several years. On top, you see a plot from a very recent study that claimed detection of hydrogen cyanide from analysis of Hubble Space Telescope observations, which would indicate the presence of a reduced hydrogen-dominated atmosphere. At first glance, it would be surprising to see such an atmosphere on an old, mature planet, because we think that hydrogen should readily escape to space. The study shown below, on the other hand, scrutinized the same data using a different analysis pipeline and could not find evidence for any spectral features, and is hence most consistent with either no atmosphere or a cloudy one. On the right, you see the sub-Neptune K218b, for which several independent analyses found evidence for water in its atmosphere, seen on top here in the spectrum, and on the bottom the retrieved water abundance for a given cloud top pressure. Both planets, and more of their size and installation class, will be observed in the near future with the James Webb Space Telescope, which may tell us something about the nature and origin of sub-Neptune exoplanets, and how they relate to the planetary classes that we observe in the solar system. On this illustration, you see the pathway of the transition from the initially hydrogen-dominated primary envelope on terrestrial and super-Earth exoplanets to their secondary atmosphere that may be dominated by higher mean molecular weight species. The primary atmosphere sourced from the protoplanetary disk during planetary formation and initially in contact with a large magma reservoir in the interior that is molten from the primordial heat of accretion and solidifies over time to a solid aggregate like the planetary mantle today on Earth. These secondary types of atmospheres are usually assumed to be dominated by volatiles delivered during accretion, and therefore the rate and form of volatile delivery is crucial to us to understand the climate of terrestrial exoplanets. However, and this is central to my argumentation, the following: there are several dominant geochemical and geophysical processes that operate in the interior of planetary mantles, specifically during the molten magma ocean phase, that can alter the primitive compositional assemblage of the planet and as a result overprint the primordial composition. Here are two such so-called redox reactions that operate in the interior that can overprint this primordial mantle composition: iron disproportionation and endogenous water production. I here focus on the former reaction, the disproportionation of ferrous to ferric iron in the deep mantle, which on Earth is thought to have largely controlled the composition of the mantle and long-term climate. This mechanism only works for planets of a given size, for instance terrestrial planets like Earth and Venus, because the redox reaction is pressure dependent. In general, disproportionation reactions are redox reactions in which one compound with an intermediate oxidation state converts into two compounds, one with a higher and one with a lower oxidation state. In this case here, the key reaction involves iron. Ferrous iron converts to ferric iron with a high oxidation state, plus iron metal with a lower oxidation state. For example, in a silicate melt, this reaction can proceed like shown here. FeO, or wustite, reacts with aluminum oxide to form perovskite plus iron metal. Why would that change the composition of the planet and affect the atmosphere, you may ask? Let's have a look at the right side at this sketch. The green symbols here represent compounds that include Fe2+, for instance in the form of FeO. Under high pressure, these disproportionate and form a compound with ferric iron plus iron metal. Iron metal now, however, is denser than the ambient mantle. In the magma ocean phase, the viscosity of the mantle is extremely low, similar to water, and hence the dense iron metal should be able to easily sink to the bottom of the mantle and be locked up in the metal core of the planet. On a global scale, This reaction then grows the metal core and leads to net oxidation of the mantle, because the mantle has lost some of its reducing power, the iron, to the core. Over time, mixing by convection in the mantle will redistribute the material and homogenize the upper and lower mantle, which is especially effective during the magma ocean phase, when convection is rapid. As I said, the atmosphere in terrestrial planets is established foremost by outgassing from the interior, and therefore, once iron disproportionation has oxidized the mantle, the composition of the atmosphere is a different one from that of a planet where no net oxidation has taken place. Importantly, in this picture, the core, mantle, and atmosphere of the planet form an interconnected system that equilibrate chemically with each other. Reducing power is transferred from the mantle to the core. This changes the overall composition of the mantle and hence the compounds that are outgassed to the atmosphere. Because the iron disproportionation reaction is sensitive to pressure, this predicts that the atmospheres of smaller planets should inherit the material composition derived during accretion. The atmosphere of planets that accrete under reduced conditions, say in the inner disk, should thus be dominated by reduced species, such as H2, CO, or CH4, and their photochemical derivatives. Larger planets' atmospheres, on the other hand, would feature more oxidized atmospheres because their interiors are altered by redox reactions that increase their oxidation states, which leads to outgassing of H2O, CO2, or SO2 and their derivatives. Importantly, however, these redox reactions establish equilibration between core, mantle, and atmosphere of terrestrial and super-Earth type planets by mixing between atmosphere and mantle and metal core. However, and this is central to my message here, the internal convection regimes in sub-Neptunes may prevent, or at least protract, net oxidation of the planetary mantle, because the transfer of iron to the core can be limited by the internal magma flow. Why? The left side equation here is the Rayleigh number, which is an expression for the fluid flow regime in buoyancy-driven flow. At very low Rayleigh number, there's no flow, and heat transport would operate by conduction. At higher values, which is relevant for planetary objects, heat from the core to the surface is transported by convection. For sub-Neptunes, the crucial parameter is the mantle column depth, which drives the internal fluid flow into extremely turbulent regimes. Why does this matter? Because highly convective systems can entrain particles of a different substance. To illustrate this, let us have a look at this computational simulation of particle settling in turbulent convection. You see the molten planetary mantle, core at the bottom, atmosphere at the top, with a temperature difference between bottom and top that drives convection. The gray and black particles in this case are silicate crystals, and the background color indicates temperature. What you see is that in certain flow regimes, the particles can be trapped and suspended in the flow. Instead of raining out and merging with the core, they follow the magma flow and are kept in the overturning convection cells. Extracting this key information here means that iron droplets that are generated by redox reactions in sub-Neptune interiors feel competition between gravity and kinetic energy that is carried with the flow and that acts to suspend the droplets in the fluid flow. We can understand this by using scaling relations derived from convection cell experiments. The upper blue formula gives the scaling for the expected droplet diameter in a magma ocean. The lower formula gives a size threshold for entrainment in the magma flow. The iron droplet size is set by competition between droplet growth versus shear stresses in the magma flow. At the same time, the maximum size of iron drop particles is set by a competition between gravity and the stresses in the magma. If d droplet is larger than d grid, iron particles will rain out. Otherwise, they may be suspended in the magma flow. This is shown in this figure, which plots the iron droplet diameter as a function of magma ocean depth, the crucial parameter that sets sub-Neptunes apart from terrestrial planets. In blue, you see the expected sizes. In red, you see the maximum sizes of particles that can be entrained in the flow. The different line styles stand for different planetary heat flows. For a heat flow of 10 to the 6 watts per square meter, the two lines cross here, for 10 to the 5 here, and for 10 to the 4 here. Left of each of the crossing points, let's consider 10 to the 5 here for example, gravity wins, rainout is possible, and iron droplets will merge with the iron core. Redox reactions can alter and overprint the primitive mantle and its composition in this regime. Right of each crossing point, on the other hand, the kinetic energy carried with the flow wins, and iron droplet rainout is quenched. This means that the chemical equilibration between mantle and core can be shut off, and the mantle is kept reduced. Idealized, this diagram here illustrates two end-member cases of magma ocean circulation. On the left-hand side, we see a magma ocean circulation regime akin to the terrestrial magma ocean. Iron droplets are not suspended, but rather rain out and merge with the core. Mixing is efficient enough between shallow and deep mantle to allow iron disproportionation or water production to oxidize the mantle. In the right regime, however, the fluid flow quenches droplet rainout. This then drives the redox reactions to local equilibrium and partly preserves the primordial composition of the mantle. These two scenarios for the flow regime predict diverging compositions for secondary atmospheres. The left predicts oxidizing compositions with high mean molecular weight atmospheres, while the right predicts reduced species. The same goes for the mineralogy of surfaces that potentially preserve a memory of this stage, and which can be probed potentially with eclipse mapping of ultra-short period super-Earth. Finally, the two scenarios qualitatively impact the lifetime and chances for detection of secondary atmospheres. The oxidized scenario prolongs magma ocean lifetimes on super-Earth because of the enhanced greenhouse effect of water vapor. Reduced atmospheres that could be generated from outgassing from a reduced interior, however, would have better chances for detection because of their larger scale heights. Regarding observational tests, here you see a synthetic spectrum for the range of 2 to 14 micron with JWST NIRCam for GJ1132b, the controversial planet I introduced earlier. You can see features of ammonia, hydrogen cyanide, and cyanoacetylene, assuming a reduced secondary atmosphere generated by the Rainout quenching regime in the internal magma ocean. This means atmospheric characterization of a few observationally accessible targets will be able to conclude on the interior redox state of super-Earth and thus start to provide constraints on interior dynamics and composition very soon. To summarize, the fluid flow regime of the internal magma ocean and sub-Neptunes could affect observational properties like composition, specifically for the atmosphere-stripped subpopulation of the Kepler radius valley. The mechanism advocated here is that turbulent magma flow can entrain liquid iron droplets and quench core mantle differentiation, which would essentially preserve the mantle composition inherited from accretion. This may then lead to observable differences that can be probed with astronomical observations. The Rainout quenched regime should feature reduced atmospheres and interiors but cool faster. The redox altered regime would feature oxidized atmospheres but prolong magma ocean lifetimes. Thank you very much for your time and attention.